So today we'll continue looking at electricity and the electric circuits topic, and we will look at the very important concept of resistance. Resistance is useless, so let's get into it. Cheers. Okay, so resistance isn't really useless. It's a very important concept we need to learn about. So resistance is a measure of the opposition to current flow in an electrical circuit. So it's pushing back against the voltage. Charge flowing through a circuit loses energy due to resistance. Sorry, there's a grammar there. In the same way that a moving object loses kinetic energy due to friction. So if we think about, pushing a toy car along a table, it'll slow down due to friction between the wheels and the table. Or if we throw a ball through the air, it'll slow down due to air resistance. So resistance is a little bit like the equivalent retarding, opposing the motion of charge, which is usually electrons, flowing through a circuit. In electrical circuits, the energy that is lost is often converted to heat to produce light, e.g. an incandescent light globe, that's one that's got a little wire in it and it gets really, really hot and it glows, or warmth in the case of a heater or a hot water service, or maybe an oven. And there's lots of other examples I could have thought of too, but it's a very, very important concept. Mathematically, resistance is given by Ohm's law. Resistance is equal to the voltage divided by the current. It's given the symbol omega from the Greek alphabet. It's sort of the Greek alphabet equivalent of O, and we call them ohms. Now, I find it more useful to think about Ohm's law in terms of this rearranged form, I equals V over R. So we've just rearranged this formula here, because this tells us the greater the voltage, the greater the current. So the more energy we give to the current, the more current that will flow. That sort of makes sense. The more energy it's got to overcome the resistance. But the greater the resistance, the less the current. So the more opposition there is to the flow of charge, the slower it will flow, so the current will be less. So current is proportional to the voltage, proportional to the amount of energy, and inversely proportional to the resistance. So either of those are acceptable ways to remember Ohm's law. I just think it's easier to remember this one in my head. I always think, current, what's going to happen if the voltage increases? The current will, so that's on top. What happens if the resistance increases? Then the current will drop. Okay, a couple of other terms we need to know about. In an ohmic conductor, the resistance remains constant as the voltage increases. So firstly, if we look at a graph of voltage versus current and we increase the current and we look at the voltage, or if we increase the voltage and look at the current, this line here, the slope of this line, the rise over run, so that slope, the rise over run, will be equal to the resistance, because voltage, the rise, over current, the run, equals the resistance. So if the slope is constant, the resistance is constant, and we call that an ohmic conductor. In a non-ohmic conductor, the resistance changes as the voltage increases. So as the current increases, the slope of this line will change, indicating that if the slope is changing, the resistance is changing, and it's a non-ohmic conductor. The resistance of a conductor depends on its length, area of cross-section, temperature, and the type of material which is used. And we can use this formula: resistance is equal to rho, which is the resistivity, times length divided by area. You can go and look at this simulation on FET, resistance in a wire, and play with this. It's a very, very simple one. But basically we can see as the length increases, the resistance increases. If L is on the top, gets bigger, R will get bigger. As the cross-sectional area increases, the resistance decreases. If A gets bigger, R gets smaller. Generally, as temperature increases, resistivity increases. As resistance increases, that probably should say. Faster vibrating particles in a material make it harder for charge to penetrate. So the main thing that will affect the resistivity is the temperature. Now in a circuit diagram, we usually indicate the resistor with this sort of zigzag squiggle line. So when we're showing a circuit and we want to show a resistor, that's how we would indicate it. Now the other thing I just want to briefly go through in the next slide isn't directly out of the curriculum statement, but I think it is very, very important. So let's move on to that. So resistors are very, very, very common components in any sort of electrical circuit, and not always, but generally they'll look a little bit like this diagram here, and generally they'll have 4 colour bands on them. And those colour bands are really important. They tell us what the resistance of that resistor is in ohms. So if we look, each colour represents a number, and, well, yeah, all of these colours represent a number. The first 2 give us the amount, if you like. The third is the multiplier, and the fourth just tells us the tolerance. And that's either usually gold, which means they have a 5% tolerance either side of the quoted value, or silver have a 10% tolerance either side of the quoted value. So if we look at the one in the example here, green is the first band. So the first number that we would have on this is a 5. Blue is the second band, so the second number would be a 6. The multiplier is red, so that's times it by 100, which would give us 5,600 ohms, and that would be plus or minus 10%. So if you look at a resistor and you look at those coloured bands, you're able to work out that value for the resistance quite quickly using that chart. Okay, that's it for resistance. We will explore a few more of these concepts later on in the laboratory when we play around with some electric circuits, but that should be more than enough to get you started. Cheers.